Okay, just to summarize what we saw here, if f maps Rn to R, then the derivative, what we're calling the derivative, is the gradient, delta f, and so that's going to be our matrix, or our vector of partial derivatives. So I'm assuming I've got n variables, and the second derivative is the Hessian. And remember that this is a matrix, okay, where HF is f11, f12, f1n. So these are the second partial derivatives. Good. All right. So in our last case, I want to talk about what happens if, maybe I'll call it G to be consistent with notes. What happens if G maps Rn to Rm? Well, for one thing, what would such a G look like? Well, G would input n variables and output m variables. And so we assume typically that there is a coordinate function for each of the m output variables. And so we could write g of x is equal to like g sub 1 of x1 through xn, g sub 2 of x1 through xn, down to g sub m x1 through xn. Good. All right. Now, when we talk about the linearization or the derivative, what are we going to be meaning in this case? Well, you can think of it as linearizing each row or each entry here. This isn't a row yet, right? This is just a vector in Rm. And so each coordinate dimension has a function, and so we can think of linearizing each one. And so the derivative is actually going to be a matrix now. And it's called the Jacobian matrix. And so the Jacobian matrix, I don't know how you want to write. I guess we'll just write JG for Jacobian of G. And so that's going to be the gradient of G1, gradient of G2, down to gradient of GM. And so this is what size matrix is this? M by N. Yes, so this is an M by N matrix of first partials. Good. Now, we don't typically look at the second derivative of that, but we certainly could. I think for the what we're doing, we'll just keep it here. So what would the linearization of G be in this case? The linearization of G. Now remember, G is mapping what to what? Rn to Rm. What is a linear map? So this is a side note, side remark. What does a linear map from Rn to Rm look like? Did you answer matrix? If you did, then you're correct. And in fact, this is the matrix. The Jacobian matrix. Jacobian matrix. I'm losing my voice. Okay, so then the g of x is going to be, well, it's going to be approximated by our linearization, g of a, so we're always basing our approximation somewhere, plus the Jacobian matrix, and that again is based at a, right? All the partial derivatives are at a, so this is again m by n matrix, and that would be times x minus a, right, which is an n by 1 vector. Good. So let's practice this on something. How about, I was just going to use the notes. Oh, that's kind of complicated. Okay, let me just make one up. How about g of x equals x squared plus 3y. How many variables should we have? Plus 2z. I'm just going to have this 2 by 3 maybe, or 3 variables in, 2 variables out. And so let's just take xyz. Whoops, xyz plus 2x. Okay, and then we'll evaluate at 1, 1, 1. Okay, and we will linearize. So g of x is approximately g of 1, 1, 1, which is 1 plus 3 plus 2, which is 6. 1 plus 2 is 3, plus, now I've got to take a side computation here. Let's take a look at our Jacobian. So the partial of number 1 with respect to x is 2x, with respect to y is 3, with respect to z is 2, and with respect to x is yz, with respect to y is, oops, plus 2. Then with respect to y, it's going to be xz, and with respect to z, we just get xy. Good. And so the matrix then, that is 2 by 3, is going to be a 2, 2, 3, I'm just evaluating my Jacobian at 1, 1, 1, 2, 3, 2. 1 plus 2 is 3, 1, 1, there we go. And then you would multiply that by x minus 1, y minus 1, z minus 1. And there it is. That is your linearization. Good. All right. Now, why did we bring up this linearization? Just for fun? It is kind of fun once you get used to it. But no, it's for the multivariate Newton's method. So that's where we'll start next. Multivariate Newton's method. All right. So, what do we want to solve in this case? In this case, we actually want to solve for where the gradient of f is equal to 0. And that is a vector, right? So that comes from our if we have like a z equals f of x, right? So now, this is why I use g in this last notation. Let g of x be equal to the gradient of f of x. Okay? Then, what we're solving for, we want to solve g of x equals 0. Right? And the idea is that you make a guess, take an initial guess. Let's say x0. You linearize g, and then solve for where the linearization, solve for where the tangent plane crosses the axes. Okay, so what would that mean in this case? We know what the linearization is, right? The linearization is g of x0 plus, what was it, Jacobian at x0 times x minus x0. And normally we would set that equal to g of x, but we want to set that equal to 0. Does this look familiar, by the way? because now x1 is going to be this number right here. And so let's see if I can solve for that variable. And so I'll go ahead and subtract. How shall I do this? Okay. Minus, I'll go ahead and fill in the steps here. Now I can't divide, right? So I have to assume something here. I have to be able to invert the Jacobian matrix. Right, and so then x is equal to x0 minus the Jacobian matrix inverted times g of x0. By the way, compare to the one-dimensional case, so this is x1. x1 was equal to x0 minus f of x0, or g of x0 divided by g prime of x0. Do you see the similarities? Yes. Does it matter if I multiply this matrix on the left or the right? Yes. Because remember that this is an m by 1, or this is an n by n matrix, right? And this is an n by 1 vector, right? So it does matter which order you do that in. And so multiplying those together, you get an n by 1 vector. Okay. And so that's what the formula is in terms of g. What is the formula in terms of our original function f, right? Because we said that g was equal to the gradient of f. Well, so multivariate Newton we're looking for the extrema of f of x, right? That is a scalar valued function right now, right? The way to do that is to take xi plus 1 equals xi minus, now this is going to be the Hessian of f at xi inverse times our gradient of f at xi. Good. And there is our formula for multivariate Newton. Okay, so in the next video we'll talk about how to implement that a little bit, and just some implementation issues, and then we'll also talk about another way of finding the minimum of a function using a special technique.